Welcome. In this session, we'll summarize the important observations about the inductor current. Let's start. Now, in the previous session, we learned the behavior of the inductor current when a source is connected or disconnected from this RL network. Now, the first observation that we have about this inductor, if the inductor has no energy stored, if inductor has no energy stored, then if we connect a source to this inductor like this, so if the inductor has no energy stored, then if we connect a source to this inductor like this, then the behavior of this current that flows in this inductor after we connected the switch at t equal to 0 is like this, means I of t will be equal to I naught of 1 minus e to the power of minus t by tau, where I naught for this circuit is Vs by R and tau is the time constant of this circuit. So this is the behavior of the inductor current, which has no energy stored initially. And if we close the switch, the inductor current flows like this and it increases exponentially. So the inductor current has exponential behavior and rises towards this I naught value. And at t equal to infinity, ideally it should be t equal to infinity. This term will be 0. So it will final value will be I naught, means inductor current will finally reach to this. But we have assumed in the previous classes that for all practical purposes, when t is equal to 5 time constants, then inductor current has the steady state value, and the steady state value here is I naught, which is equal to Vs by R for this circuit. So the steady state value ideally is at infinity, means when t becomes infinity, then only this term is 0. So we will get the final value will be I naught. But for all practical purpose, we assume that the steady state arises in 5 time constants, means when t becomes equal to 5 tau, then the value of the inductor will be in steady state, and the steady state value of the current will be Vs by R. And at this time, means when the inductor is in steady state, it stores the maximum energy. The inductor stores the maximum energy, stores maximum energy, and the value of this energy is 1/2 of L I square, where L is inductance and that is the steady state value of the current. All right. So this we learned in the previous session. Now the second important observation is if inductor has no energy stored initially. So if inductor has no energy stored initially means when we connect to the switch with this, then the current behaves as given above. So the current that flows there is I naught 1 minus e to the power of t by tau, where tau is the time constant of the circuit, and I naught is the steady state value of this current, and the voltage across the inductor will be equal to Vs e to the power of minus t by tau. Now the value of the inductor current at t equal to 0, means I of 0 will be equal to 0. V of 0 is equal to Vs. Now from this observation, we see if the inductor has no energy stored, inductor behaves like an open circuit. So inductor behaves as an open circuit at t equal to 0. So inductor behaves as an open circuit element because we know there will be no current flowing if the circuit is open. So inductor behaves like an open circuit. Same way, the steady state value of the current is I naught, means which is not changing with time now, and V of t in steady state is how much? This term will be zero in steady state. That is zero. So from this observation, you can see in steady state, it behaves like an, so in steady state, inductor behaves like a short circuit. Actually, a current source, but we can, for time being, we can say it behaves like a short circuit. So it behaves like a short circuit. From this VI observation, it behaves like a short circuit. There's no voltage, but there is current flowing through this element. So it behaves like a short circuit. Now, the third important observation that we have about this inductor that we learned in the previous session is inductor current cannot change instantaneously. Inductor current cannot change instantaneously. Instantaneously. What do I mean by this? Means whatever is the value of the inductor current just before this switching. Switching is just before the switching is denoted by 0 minus. The value of the inductor current will be same after that, just after this switching. All right, this is the meaning of that. This inductor current cannot change instantaneously. Now, the fourth important observation is when we remove the supply. In other words, when we remove this supply here and connect this RL circuit like this. So if we have inductor that looks like this, and if we change the position of the switch from 1 to 2, and the inductor was initially charged to current I naught, means when this was in position 1. Now, if we change the position of this switch from 1 to 2, then the inductor loses its energy. Then the inductor loses its energy, and the current decays exponentially. And the current behavior is given by this I naught e to the power of minus t by tau. This is the value of the current at the time of that when you change the position of the switch from 1 to 2. This will be the value of that current that is stored in this inductor. All right. In other words, when I change the position of the switch from 1 to 2, inductor behaves like an active source because now this is delivering the current. It behaves like an active element in the circuit, means in this RL circuit. Then it behaves like an active element and it delivers the energy to this resistor, and that decays, the current decays like this expression. And at steady state, we assume it arrives after 5 time is equal to 5t time constants. Then that energy stored in the circuit is equal to 0. The energy stored in the network is 0. So these are the important observations that we learned from the previous sessions. All right, let me end this session here.